Okay, so today we're looking at some application and proportion problems. And, word problems tend to be the least favorite, but oftentimes if you have some example to follow or some explanation on how to solve these, then we can go ahead and they turn out to not be quite so bad. So the first problem I'm going to read to you here. It says a commercial contractor needs to clear a plot of land for a new bank. Ryan can clear the lot in 7.5 hours. Ethan can do the same job in 10.5 hours. If they work together, how long will it take them to clear the land? Okay. Now, typically, if you are working out problems where, one person can do it a certain amount of time and then another person can do it a different amount of time, how long will it take them to complete one job? And so the way that you can think about this is if they're working together, so x over some number a plus x over some number b is equal to one job, okay? So now if we plug in what we know, and we'll just say that here Ryan is A and Ethan is B, we simply would have x over 7.5 plus x over 10.5 equals one job. Okay. Now, to do this the good old-fashioned way, we would simply want to convert those decimals into actual numbers. So I'm going to multiply everything on the bottom by 10, or another way to think about it is multiplying everything by 1/10. Okay, so then I have x over 75 plus x over 105 equals 1/10 of a job. Okay. So now we have to find a common denominator. And you might be inclined to want to just multiply things together. I actually just found the common denominator by adding up 105 and then finding something that 75 would go into. So that didn't take me very long to do. And I found that the common denominator was 1,050. Using that common denominator of 1,050, 50 equals 1,050. And then, of course, we have to find our numerators. So I know that 75 goes into 1,050 14 times, so this becomes 14x. I know that 105 goes into 1,050 10 times, that becomes 10x. And I know that 10 goes in 105 times. Now, what we want to do at this point is to clear this fraction. And how I do that is I simply multiply everything by 1,050 over 1. And what that does is it gets rid of the whole denominator. And then what we're left with is our numerator. So I have 14x plus 10x equals 105. Sorry about that. It looks like I forgot the 5 up here. There you go. So then we simply add them up and solve for x. So 24x equals 105. Divide both sides by 24, and we'll find that x is equal to 4.375 hours. So that's if they do the job together, that's how long it would take. So again, if you go back and you look at that first initial equation. Okay, so this was just simply a proportion problem, and I can't tell, I'm sorry if this is repeating myself. It looks like my recording had stopped, so I apologize for that. So what this problem is a proportion problem where it was telling us that the length of a real Indy car is 15 feet and that the width is 7 feet. And then it was saying that the die-cast models that you would see in the store, like Hot Wheels, the width is 3.5 inches, and what would the length be then if it was to be the same proportion? So I chose to convert the length of the real car to inches and the width to inches, and then we could set up a proportion. Everything has to be in the same units here. So I took the length of the model all over the length of the real car equal to the width of the model all over the width of the real car. And then we were able to solve for x here and get 7.5 inches. So now we're going to look at a distance equals times time problem. Okay, so the problem reads like this. The speed of the current in the Wabash River is 3 miles per hour. Okay. A kayak can travel 4 miles. So the distance up is 4 miles. In the same time as the distance down, which is 10 miles. And what they're asking us to do is to know what is the speed of Brooke's kayak in still water. Okay? So in other words, how fast can she paddle if there was no current at all in the river? And so we have to remember a couple of things here. Distance equals rate times time. Okay? Now, the trick with this is that we have two different distances. We're also going to have two different rates, but we want to find the rates in still water. The time here is going to be the same, okay? So you can think about it like this. If the current is 3 miles per hour, that means when she's paddling upstream, she's going against the current, okay? So the upstream current would look like the rate in still water minus 3 because you're going against the current. The rate going downstream is going to look like R plus 3 because you're going with the current. Okay, so if we know that the time is the same, then basically what we're looking at is something like the R times T upstream has to equal the rate times the time downstream. Okay, now the time is the same. The distances, however, are different. Okay, so if you were to solve this, and we want to solve for the rate, then we're going to go ahead and just set up some equations. So, for example, I know that if I have, because t is 1, I can just not worry about that. I know that d over r one way equals d over r the other way. So, let me show you what that looks like. So if you have distance over r one way has to equal the distance over r the other way. So plugging in what we know for upstream, downstream, we could say the upstream would look like 4 over r minus 3 has to equal 10 all over r plus 3. And solve. Okay? So we would have, multiplying both sides, r plus 3, r minus 3. And same thing all the way around, then will give us this. So we'd have 4 times r plus 3 is equal to 10 times r minus 3. And that will give us 4r plus 12 is equal to 10r minus 30. I'm going to go ahead and solve here. So I'll subtract 12. And that, I'm going to go up here now. So that will give me 4r is equal to 10r minus 42. Now take the 10. Now take the 10r off. So you have minus 6r is equal to a minus 42. Minus 6, minus 6. Solve for r. You get r is equal to 7 miles per hour. Okay, so that's the rate in still water. I hope that that makes a little bit more sense. As always, please let me know if you would like additional examples.